Hello, this is Dr. Christy Patton-Lokes, a chemical engineering professor at Missouri S&T. This series of lessons is for Chemical Engineering Thermodynamics 1. We are looking at Chapter 4 on entropy, and in this lesson we're going to begin looking at the Carnot cycle, which is a principal way that we understand the second law of thermodynamics. We want to look at the first cycle, okay? And this is an invention from 1712, the Thomas Newcomen steam engine. And in this, what we see is over here we have a piston that contains steam, and that steam, as it is heated, it will expand, right? So the volume will increase with added heat. And that is attached to this bar, which is connected to this wooden beam. So as this expands and moves upward, it's going to move the right edge of the beam up, which is going to lower the left edge of the beam, okay? And that's going to drive a water pump. And as the steam then is allowed to cool inside the piston, it's going to shrink again and come back down and raise the piston on the water pump. And then you heat it again and it goes back and forth, okay? So this really was, in some sense, the first cycle, something that worked repetitively to complete a task. SADI Carnot in 1824, he was a great thinker, and he spent a lot of time thinking about ways that you could possibly build that better engine, among other things. And he was not the only one. There were a lot of people that were working on improvements to the engine, but his goal was how to maximize the efficiency of an engine. So we need to define efficiency. A simple definition of what efficiency is what we get out of a process or a cycle or a piece of equipment divided by what we have to put into it. In this case, what we're going to get out is the net work or power. And what we put into it is going to be the heat transfer into this system, right? So we were heating the steam in the piston in the Newcomen engine, and we got out the power to drive that pump, work that pump. Now, I have defined this so that these are all positive, so therefore, if it's work out, I need to take an absolute value so that thermal efficiency will always be a positive number. And so based on this definition of efficiency, Carnot came up with his hypothetical engine, not one that could really be built, but what would be the best possible way to do this. And what he envisioned was 2 reversible isothermal steps and 2 reversible adiabatic steps. So if you begin, say, with point A here, we begin with isothermally heating this material in a piston cylinder, which would cause it to expand, and then stop the heat transfer and allow it to continue the expansion adiabatically. And then we would need to reverse this, so we would compress the material, and then that would do that by cooling, and then we would adiabatically compress it, and that would take us back so that the material inside the piston was at the exact same state as it had started. So this would be a cycle, and every step here would be done reversibly. If we look a little more closely at this Carnot cycle, we have 2 reversible adiabatic steps. Those are from B to C, okay, and from D to A. And we've seen in previous lessons that based on the definition of entropy, This means that delta S for these steps must be 0. Reversible and adiabatic implies that something is isentropic, okay, constant entropy. We also have 2 reversible isothermal steps. These are steps A to B and C to D. Now, from A to B, this is happening at a high temperature. And we are going to, if it's going to be done reversibly, we know that it has to be isothermal, because if there is a delta T, it's not going to be reversible. Okay? So therefore, from A to B, it's going to be at a constant T sub H, and heat transfer is coming in. Okay? We also have C to D is being done at a cold temperature, T sub L, and that is heat transfer going out. And I'm going to write a C for cold for that. So TH and TC, QH and QC for hot and cold. Now these are reversible. And what we know is that delta S is how dq reversible happens with T, okay? But T is constant, so T can be brought out if it's isothermal. And therefore, this is simply that heat transfer for the step divided by the temperature it occurred for, only for isothermal. Okay, so the key here is that this has to be isothermal. That means that delta S from A to B is going to be QH divided by TH, and T is always positive. Q in this case is positive, so therefore delta S must be positive. And delta S for the process CD is QC over TC. QC, we know, is less than 0. Now, don't be alarmed that this is less than 0, because this is simply for the process. Clearly, if this is reversible for the universe, then delta S to the surroundings must be positive to make up for this loss in entropy in the system. So this does not violate what we've learned so far, just simply for this process, it is less than 0. So what happens if we look at delta S for the complete cycle? In this case, our system is going to be the piston in this case, or whatever we are using for our equipment. But for the cycle, it's going to be for the process AB, plus for the process BC, plus for the process CD, and then returning to the original state, the process DA. And we know that for AB, this is going to be QH over TH. For BC, it is 0. For CD, it is QC over TC. And for DA, it's also equal to 0. Okay? However, S is not path dependent. This is a state property. So delta S for the process from A to B to C to D back to A, these are the same state, and so therefore delta S has to be 0. That tells me therefore that QH over TH plus QC over TC has to equal 0. And I can rearrange this several different ways, but one way I can do this is that QH over QC is equal to negative TH over TC for the Carnot cycle. Let's next use this to look at the efficiency of a Carnot cycle. Now recall that we've already said that thermal efficiency is the net work over the heat transfer N, which is Q sub H. And to understand this a little better, let's look at the first law for this cycle. Since this is a closed system, these pistons and cylinders, delta U plus delta KE plus delta PE is equal to Q for the cycle plus W for the cycle. But by the same logic, we just said that delta S for the cycle had to be 0. We're returning to the same initial state. Each of these state properties must be uniquely 0. And so therefore, Q cycle plus W for the cycle has to equal 0 for any cycle. This is true for any cycle. And therefore, we can say that if I look at it over the cycle, the total amount of heat transfer is equal to the negative of the total amount of work produced in this cycle. In this case, QH plus QC, the total heat transfer in the cycle, is going to be the negative of the net power for the cycle. Thermal efficiency, again, is the net work divided by Q sub H. That's our heat transfer into the system. W net is QH plus QC divided by QH. And I could rewrite that, right? I can divide QH into each of those. Say 1 plus QC over QH. QC is negative, QH is positive. So this is 1 minus, if I did the absolute value of those. And then we know that this is true for any cycle. Okay. And for a Carnot cycle, we have said moments ago that QC over, actually we said QH over QC is equal to negative TH over TC, or if we were to do this in absolute value, the QH over QC in absolute value is equal to TH over TC. And so for a Carnot cycle, we end up with 1 minus TC over TH. Right, we had QC over QH. And this is going to be our result for a Carnot cycle. This is a general definition. We also could do this if we have only 2 heat transfer steps. But this is true for reversible, and this is true for always. So this concludes this lesson on the Carnot cycle. And we are going to look at ways that we can begin applying this to some simple problems that will help us to understand the second law and what it has to do with the way that the world actually works. Thank you very much for your time.